it will be better explained with the help of an example. So, to compare the value what we get by this approach, that is Rayleigh's method by Gramel's modification, let us take up again a simple problem of a cantilever beam uniform, for which we know the answer. Only thing our objective is to compare the Rayleigh's method and Rayleigh's method using the Gramel's approach. Just to demonstrate that, we will take a simple, and we can also compare the exact value of the answer. Let us take a cantilever beam of uniform cross section and of length L. They are all uniform. Now, we assume the deflection satisfying the condition, at least the geometric conditions will have to be satisfied, you know that. So, we just take it like this. So, the slope is, and X, we don't need that anymore. So, let us see, of course, we can do that. At x is equal to 0, x is equal to 0, that it satisfies the condition. The slope is also 0. That is another geometric condition that is also being satisfied. At the free end, we are supposed to have this as 0, this is 2c, this is 0. But it should have been 0 because there is no moment acting here, but it is not satisfying this condition. But anyhow, it is satisfying the geometric boundary conditions, which are very important and they must be always satisfied. Now, with this, what will be the inertial loading? Inertial loading is x square. It will be like parabola. And we consider an element of length d zeta at a distance zeta. Now, let us find out the moment of this inertia force because of this produces how much bending moment at distance x from the origin. So, what is the inertia force of this element? That is equal to the mass of the element, that is A into d zeta into rho. Then omega square into x a square. Now, x a is this part, so it will be c x square whole square. So that is the inertia force. And moment of that at x is equal to x due to this element will be omega square a rho c square x to the power 4 d zeta into this distance is zeta minus a. I am sorry, this is not omega square. So this will be Cx. So this is a force, inertial load, and this is the distance. So this will be the moment, and since this moment is our positive direction of moment was like this, and for that the slope of the neutral axis as x increases gradually decrease. Here it will be gradually increasing, so there will be a negative. So therefore, moment here, total moment will be the moment of all the inertial loading of all the elements from zeta is equal to x to zeta is equal to L. So therefore, moment as a function of x at x distance x will be minus omega square a rho c x square zeta minus x d zeta x this is the absolute zeta. So we have taken the coordinate system as zeta, it will be zeta. Zeta is the variable, not x. X is a parameter. At x, zeta is equal to x, what is the bending moment? We want to find out at this stage. So this, if we estimate, we will find this is coming to be minus omega square rho a c by 12 into x to the power 4 plus 3 L to the power 4 minus 4 x L cube. Now, if we use this, omega square is equal to m square by EI dx x 0 to L. Again, now x is the variable, 0 to L rho a x square dx. If we now use this m here, and x of course is we have assumed like this, then this will lead. Now of course you should remember there that omega will also come in this side because of this, as omega to the power 4. So when you solve the whole thing, we will get omega square is equal to 12.46 1 by L4 EI by rho e, or omega is approximately square root of this 3.531 by L square root of EI by rho E. So this is the result we get using the Gramel's modification. That means we find out the moment at x due to the inertial loading which is caused by an assumed deflection xa, and substitute it here in the original equation of Rayleigh, and then solve the equation for omega square, because omega square will be on both sides, and we get this. Now if we try to find out the with the same function or same displacement function xa, just following Rayleigh's method, just by Rayleigh's method if we take, then what we get? Omega square is simply 0 to L EI d2 xa dx square square. Now we know dx square dxa is 2c. So this will be simply 4c square into EI dx, that is 1 by L, that is the numerator. And what will be the denominator? Rho A x square, that is c square, x to the power 4, if you integrate it will be simply L to the power 5 by 5. So that is 20 EI by L4 rho A, or omega is approximately square root of 20 is 4.47. So this is the value we get by using simple or straightforward Rayleigh's. And for a cantilever beam, we have already solved by exact method, and the exact value we already calculated earlier, which was equal to now if we compare, this is the exact, and using this simple straightforward assumption about the displacement function Cx square, the Rayleigh's principle gives this, and using the same assumption about this, if we use the modification proposed by Gramel, we get this. And now you can see that how close it goes to the exact value. So therefore, the accuracy can be substantially improved in the Rayleigh's method if we use the moment expression directly, which is determined by finding out the inertial loading based on the assumed mode shape x, and that results in substantial improvement of the value of the result. So I think this will be enough for the time being, but we have to now keep in mind that whether it is possible to find out the higher mode or higher frequency. All these cases, this Rayleigh's principle is valid in case of fundamental frequency, as you know. So therefore, we are getting all the time, we are assuming something for the first mode deflection. If we can find out the second mode shape and put it there, obviously we will get the second mode, but most of the time we see that it is convenient to solve the problem satisfying the boundary conditions, which will give us the first mode frequency. So in the next presentation we will try to see if it is possible to get a methodology by which we can have some approximate values of the higher frequency. So, following the approach proposed by Rayleigh and even considering the modification suggested by Grammel, it is always found that we get the fundamental natural frequency or the first mode natural frequency. However, when it is required to find out higher frequencies or higher mode frequencies, it is possible to devise a method of this approximate nature following the same principle and employing one of the important properties of Rayleigh's quotient. We have seen that Rayleigh's quotient is equal to So, this is the maximum potential energy during normal mode oscillation, and this is the maximum kinetic energy divided by the natural frequency square. So, this is the Rayleigh's coefficient, and we treat Rayleigh's coefficient as the natural frequency omega square of that. And the maximum potential energy expression will depend whether it is a transverse oscillation. In that case, it becomes if it is longitudinal oscillation, then again its expression is different, we have seen. So, therefore, in general, we can keep it as the maximum potential energy during a normal mode oscillation divided by this quantity. Now, there is one property of this Rayleigh's quotient which says that so, whatever we may assume for this displacement function or the deformation pattern or mode shape, whatever we may say, R of this quantity will be always higher than a quantity which will be minimum or stationary as Xa becomes a real mode. That means exactly it coincides with the natural mode. So, therefore, the omega square what we will get, which we associate with this omega square will become lower and lower as Xa becomes a better and better approximation, and when Xa becomes indistinguishable from the exact mode, then the real natural frequency will be the lowest. So, this property of Rayleigh's quotient is used, and this proposal was first suggested by Ritz, and the whole process is therefore called Rayleigh-Ritz approach. So, in Rayleigh-Ritz method, this assumed deformation shape is expressed in the form of a series or in terms of a number of functions so where each xi satisfies the boundary conditions as much as possible. Here, better approximation means satisfying more boundary conditions, better results will be obtained, and at least the geometric boundary conditions. Now, if we do that, then what will happen if we substitute? This is also a function dependent on quantity dependent on xa and derivative. Here also it is dependent on xa. So, as a whole, when this quantity is found out, so the Rayleigh's coefficient will be equal to, for transverse oscillation, in beam mode, so when you substitute this, this becomes a function of C1, C2 up to Cn. So if all are these xi's are definite functions, E, I, rho, A, these are all known quantities, L is known. So only thing what remains as a parameter on which R will depend will be the n number of coefficients. So now, if R be a function of all these coefficients you have chosen, so what will be the best way to select these coefficients? Here comes the utilization of this property, that we should select C1, C2 and so on up to Cn in such a way that we get the minimum value of R. That means it will be nearest to the real value of the natural frequency square. Thus, the condition which satisfies that they are so chosen that because R will be always higher than the natural frequency square you have seen. So the best possible choice of R for a given value of or given functions xi's can be those for which C1, C2, Cn are so that R is minimum. and that condition says thus so del r del Ci will be equal to 0. If r takes a stationary value at the chosen coefficient, then this all these dr dC's, there will be n number of such will be all 0. Therefore, this represents n number of homogeneous equations in C's, and therefore a non-trivial solution of the C will be possible only if the determinant is 0. So therefore, when this is done, so this represents this n equation. So the now the determinant of these equations, if we differentiate this is the numerator and this is the denominator, will be this. How do we get it? Is that if this is the numerator, let us consider this as the numerator and this is the denominator. So del r del Ci will be equal to, so this will be del n del Ci by d minus, this will be n by d square del d, and this is equal to 0. So what we can do, this gives us, below there will be d square, so there will be d dn dCi minus n since d square is not 0, this itself gives us d and this is nothing but that. This is the numerator and this is the denominator. Now, we further know that omega square is equal to, this is the denominator, this is the numerator. So we know that omega square is equal to numerator by denominator. So when we use this quantity here, then using this, now of course we should remember that I is equal to 1, sorry, here of course it is so these equations we will get it 0 using this in the above equation. What we get finally, so there will be now n such equations. It is very easy to see if we use this, so therefore we can always take this common, take out this. The moment we take out this, it goes below here and this becomes omega square. So it becomes omega square and then this remains. So therefore it is straightforward. So then what is done, that these n equations in Ci, C1, C2, C3 up to Cn, and these homogeneous equations can have a solution only when the determinant becomes 0. We will try to explain the whole process with the help of a specific example. Let us take the same case of a tapered beam. We have found out the fundamental frequency by Rayleigh's method, with Gramel's modification. We also know the exact value. So it will be easier for us to assess our answer which we get from this, at least the first mode. So what we will try to do, because we have to keep our analysis and board work less, and also objective is to demonstrate the use of the principle to find out higher mode, we will take only a case where we will find out up to second mode. So the example is the same. The same problem. The tapered beam, the height of thickness is varying linearly and reaching the value h after a length L, and it is symmetric. So we fix the coordinate here, the origin and the x-axis. Now the question comes that we have to, if we are interested only up to 2 modes, say omega 1 and omega 2 only. So therefore, we would need only 2 terms in the expression x8. Like this. And x1 and x2 should satisfy the boundary conditions, at least the geometric one. So what we do, we select x1 as so these are the two functions of x. At x is equal to L, x1 is equal to 0. If we differentiate once with respect to x, again this term 1 minus x by L remains, and at x is equal to L that will be 0. So slope is also 0. So these are the two boundary conditions, geometric conditions is satisfied. This one also say at x is equal to 0 also it is becoming 0. So it is not really satisfying the conditions. But other end, if you see that x is equal to L, it is satisfying, and it both the slope and the value of x, deflection is 0. So therefore, x1 and x2, x1 is satisfying the geometric conditions, x2 also is satisfying the geometric conditions at this end, but x2 is not really, neither x1 and x2 will satisfy all conditions. Anyhow, our objective was that whether it satisfies the two conditions here or not. So we have kept that in mind. Only two conditions are being asked to be satisfied. Now, with these two things, our equations become so we substitute this quantity, which becomes this after integration of this, and this becomes, after integrating, becomes this. So now this yields two equations. These two equations will be now algebraic equations. So here this Ci, so therefore if you differentiate with respect to C1, we get this equation. Now if we differentiate with respect to C2 partially, we get the other equation. So now these are our final equations, homogeneous equations in C1 and C2, and as I have been mentioning that non-trivial solution will be possible only when the determinant of the coefficients equal to 0, and we can see the determinant of these coefficients contain this term omega square. So this will ultimately give us an equation in omega square. So the determinant of this, if we find out, so the for non-trivial solution, this becomes like our characteristic equation, and or this becomes so this quadratic equation in omega square we ultimately obtain. Lambda, just in a short form where lambda is equal to this. Solving this equation, we get two values of omega square, and one value is omega 1 is equal to this is the first mode frequency, and omega 2 will be we get the second mode frequency also, which is approximately 5. If we try to compare this, the exact value, if we remember, thus we find that here the difference is only in the third decimal place, and that too again, so you can see it is less than 1%, maybe 0.1%. So therefore, the first mode we get quite accurately. The accuracy of the second mode has to be again found out by analysis, but it can be shown it is also reasonably accurate. We could find out even higher frequencies, only then it will be necessary to take or add one more term here like C3 X3 and take X3. Obviously, computation will be more. There will be 3 equations in C1, C2, C3, and the determinant will give rise to a third degree equation in omega square, so it has to be solved for the root. So this brings us to the end of our discussion on approximate methods for solving continuous systems, which are otherwise difficult or otherwise not so easy for solution using analytical exact method as we have discussed. I think normally what is done, a real life system will be approximated by a model system, and in the model system one tries to keep as many parts idealistic as possible, and then of course in some cases it may not be possible to have a theoretical solution or analytical closed form solution, and approximate methods like this can be used to make a quick estimate. However, nowadays with the advent of computers and computer power being so cheap, generally a complicated structure can be always modeled, and using a finite element technique, a complete vibration analysis can be solved. Standard softwares are available. In spite of that, the designers sometimes may find this quite handy and convenient for getting approximate answers.